Sorry I'm late. Okay, well, today is another basics playlist video. We're following on from pH and KH understandings, alright? So if you don't understand those fully, go back and watch those videos first. Because in today's video, we're going to dive into one of the most misunderstood topics in aquatic plant science. And that is how carbon actually behaves in the water. So we're going to look at CO2, bicarbonate, carbonate, pH, and what all of that means for plant growth. Because if you've ever wondered why some plants can thrive and do well in hard alkaline water whilst others need soft acidic water, hopefully this combined with the pH and KH will make all of that click together. So if you want a beautiful little planted tank or a huge aquascape, you're going to need to understand this. So, the carbon system in water. When carbon dioxide dissolves into water, it doesn't stay only as CO2. Whether that's from the atmosphere or you've injected it, doesn't matter. It becomes part of a dynamic chemical system that we call dissolved inorganic carbon. Yes, DIC, leave it there. You have CO2, you have H2CO₃, you have HCO₃ negative and CO₃² negative. So those are the four main carbon species which you understand if you've just watched the KH video. CO2, molecular carbon dioxide. H2CO₃, carbonic acid. HCO₃ negative is your bicarbonate, and CO₃² negative is your carbonates. And it's in equilibrium. It shifts up and down. So these species, also with the atmosphere and precipitation, they move backwards and forwards depending on the water's pH. So they're all trying to constantly maintain this equilibrium, but what's required of that equilibrium is controlled by the pH. So how does it do that? Well, at low pH, the dominant form is molecular CO2. Under 4.5, if you've watched the pH video or KH video, it's all that. Okay, but as the pH rises, it grabs hydrogen ions and turns into bicarbonate, and then even further into carbonates. Over pH 12, all carbon is carbonate species. So in high pH water, it is true to say that the amount of CO2, the molecular CO2, drops dramatically. But just like the prison analogy on the KH video, the carbon's still there. It still exists in the water, it's just in a different chemical form. It's a different prison cell. It might not be maximum security, it might be an open prison, but it moves depending on what's required. Now, what forms of carbon can plants actually use? Well, all aquatic plants require molecular CO2 to perform photosynthesis. So this liquid carbon is not doing anything. However, many species have evolved specialized mechanisms that allow them to use bicarbonate when the molecular CO2 levels are low. So they're able, at the surface of their leaves, to dissociate that hydrogen ion and then extract what they want, which is just the CO2. So being able to do that and convert it back into CO2 directly on the surface of their leaves is incredible. And they're very, very common. We're talking Vallisneria, we're talking Elodea, we're talking many, many pondweeds. In fact, quite a lot of normal, common aquarium stem plants do this. And this is why you get sort of like easy plants that cover a broad range of pH. However, this is where the problems start. Some species cannot use that. They rely solely on and exclusively on molecular CO2. So in high pH, high alkaline water or environments, they will struggle. Mosses, liverworts, delicate stem plants, Cryptocorm mioia, we keep that with the zebra plecos, does absolutely brilliantly, loves the high temperatures, can't do hard water. Now, what actually happens to the CO2 produced in substrate? We've all seen MD fish tanks put stuff in the bottom because it releases CO2. Now, when organic matter breaks down, it's true that it releases CO2. The microbes that are breaking it down release CO2. This CO2 dissolves directly into the pore water surrounding the plant roots, and although some of them can uptake CO2 from the roots, the leaves are predominantly where it's needed, where it's required, where it's absorbed for photosynthesis. So a common question is whether this CO2, once it reaches the water, is immediately lost either at the carbon system or to maintain the equilibrium between atmospheric and dissolved CO2. But the answer is no. CO2 produced deep in the substrate stays in the substrate long enough to be used partially by the roots and then in the water column until it reaches the surface, because it can only escape once it reaches the surface. Until then, it remains part of the dissolved inorganic carbon pool. It's part of your DIC. So this is why the Wallstad method works. There's no flow, so it takes a long time for that carbon to get through the stratified water. If you've got high flow, it doesn't do quite as much. And I mean, it's drastically reduced. Now, carbonate hardness, or KH, influences how strong the water resists pH changes. In high KH water, the pH is usually higher, which means most of the carbon will be in the bicarbonate form. This is why the hard water plants can use the bicarbonates. So the real question really becomes, is that carbon still usable for plants? And like we've just discussed, the answer entirely depends on which species of plant you're keeping. If a plant can use bicarbonate, hard alkaline water is rich in that available carbon for that species. The carbon is absolutely not lost or useless because it's bicarbonate. They know how to extract it. They may grow better in high KH conditions. Now, if a plant can't use bicarbonate, high pH dramatically reduces the molecular CO2, so there isn't as much CO2 in the water for them. So most of the carbon, even though it's still there, it's chemically inaccessible. It's sort of irrelevant. The growth will slow, and in very low CO2 situations, it will stop. So what do we really need to take away from this? I guess the essential message. High pH does not remove CO2 from the water. It simply changes the carbon species. It will turn it into carbonic acid, bicarbonates, carbonates, and it can always move back down. So you really do need to pay attention to what your water's doing for the choice of plants you have. So plants that can use bicarbonates thrive in hard alkaline water. Plants that can't will struggle unless supplemental CO2 is added or the pH is lower. Now, injecting CO2 generally does both, because if you watch the pH video, you understand the free hydrogen ions lowers the pH and it's moving your carbon system down again. So it's lowering the pH, okay? Now, if you find any of this useful, please let me know in the comments. If you've got any questions, let me know in the comments. Please consider liking and subscribing. It costs nothing. And as a growing channel, really early on in its infancy, it would be a huge help. Thank you very much. As always, I hope you found a reason to smile today. And more than that, I hope you find a reason to make a stranger smile.